Hello everyone and welcome to the webinar on sequential analysis driven reset optimization to improve power, area and routability. This shall be a technical webinar, but before starting the webinar, a brief and quick introduction to PowerPro Low Power Platform, which is a unified platform for maximum RTL power reduction and accurate analysis. The PowerPro platform is based on patented sequential analysis technology, which allows PowerPro to look across more clock cycles than other tools and approaches. PowerPro platform provides the best RTL dynamic power reduction tool. It has been the market leader for many years now. PowerPro has a wide range of RTL power reduction techniques, including clock, memory, and data path operators gating. PowerPro platform provides both guided and automated flows for power reduction. It can write out the power optimized RTL automatically, and it also provides suggestions which can be used by the RTL designers to manually optimize their RTL. PowerPro platform also has the capability of performing fast and accurate power estimation. It can perform the estimation both on RTL and gate level designs. Let's have a look at the agenda for today's webinar. Initially, we will look at why the resets are required in the design. Then the webinar shall delve on the motivation for focusing on redundant reset optimization. That is, why redundant reset removal is important. Then we will shift our focus to some of the existing techniques to identify redundant resets in the designs and their limitations. Then we will talk about the patented sequential analysis techniques to identify redundancies in the RTL across multiple clock cycles and reduce power of the design. And finally, we would discuss the proposed redundant reset optimization solution, which is based on the observability-based sequential analysis technique. Then we would showcase some of the results of reset optimization on large industrial designs and a brief summary of all the salient points from the webinar to conclude the session. On this note, let's start with why resets are required in the designs. Resets are essentially used to initialize the state of the memory elements, typically registers, at the system startup or for simulation. Resets also provide a convenient way to force the system into a known state for stable operations in case of an unexpected error. This would avoid the SOC to power on to a random state and get hung. For instance, many data path communication ASICs are designed to synchronize to an input data stream, process the data, and then output it. If this sync is ever lost, all the registers in the ASIC are reset in order to require the synchronization. Having established the significance of resets in the designs, we shall now look at various types of reset schemes used in hardware designs. Two types of reset schemes are prevalent: synchronous resets and asynchronous resets. Synchronous resets affect the state of the register only at the clock edge, as the synchronous reset is sampled with respect to the clock. This is a simple Verilog RTL for a register FF, which is inferred as a register having synchronous reset by the synthesis tools. The output of the register FF will be changed only with the passage of clock. To get the effect of the reset should be wide enough to be captured by the next passage of the clock CLK. Asynchronous resets, on the other hand, can change the output of their registers at any time, as asynchronous reset is sampled independent of clock. This is the sample Verilog RTL for a register FF, which is inferred as a register having asynchronous reset by the synthesis tools. In this case, as opposed to synchronous reset, the reset signal is present in the sensitivity list of the register assignment. Having established the need for the reset in the design, let's look at the motivation for redundant reset removal. Indeed, as the title suggests, power is hot. Be it the mobile communication domain or even the mobile computing domain, where on the power dissipation side, heat is a hindrance for mobility, while on the energy consumption side, battery life is of extreme importance. Also, for the high performance computing, energy consumption is critical, both for cost and complexity reasons, especially when related to cooling solutions. And of course, the networking domain or the internet, which is the backbone of both these domains, where reliability and availability are the major concerns. So indeed, it does affect everything and everybody. Let's now see how a modern SOC platform looks like and its various constituents. It will help us understand the importance of reset network in the context of full SOC. It contains registers, combinational computational logic, clock tree, and reset network, on-chip memories, customizable processors, DSP, and CPU GPU modules, IPs, macros, analog subsystems, and third-party cores. The shrinking form factors force us to pack more and more data into less and less, and as a result, the occupancy rate of registers has been ever increasing. Due to this, the reset network is also becoming larger, which shall be the focus for this webinar. Typically, only a subset of registers in the design requires reset. At the same time, finding the optimal set of registers to reset is a very complex problem, and it can require significant manual effort. As we know, uninitialized registers can result in erroneous design behavior. The designers invariably tend to apply resets on significant more number of registers than it is actually required. In fact, there are RTL coding guidelines which mandate designers to add resets for all the registers in the design, like ISO 26262 standard for automated safety. However, this indiscriminate addition of resets on registers has its own penalty. Registers with reset require bigger technology cells to be implemented and hence increase area and power of the design. This is a sample circuit for the D-type register without reset. Here the input data D is copied to output Q when the clock input is active. Now let's have a look at the circuit for the D-type register with preset and clear. Here both the preset and clear inputs are active low asynchronous reset signals. With the inclusion of these signals, 3 input AND gates are required in the register logic as opposed to 2 input AND gates for the registers without resets. Hence, it leads to significant increase in the area and power of the design. With the increasing design complexity, typically large number of registers are used in the design. If all or most of the registers in the design happen to have resets, then the reset network would have to be routed to those registers as well, and it would have a very high fanout. Its routing while meeting the timing is a challenging task, which would entail heavy usage of buffers and inverters. This large reset network can adversely impact routability of the design and lead to timing and congestion issues, as can be seen in this snapshot. At the same time, if most of the registers in the design have resets, then in the reset phase, large rush current would flow in the design, which can burn the chip. This clearly indicates that we need a solution to remove the redundant resets in the design. Designers have been using variety of techniques to remove the redundant resets in their designs. We shall now briefly look upon some of the important existing techniques practiced in low-power SOC designs. All of these techniques are manual and none of these are automated. Let's look at the first technique. This method involves forcing reset value of a register and then performing the constant propagation in the design in the fan-out of this register. Based on the result of the constant propagation, there would be some of the registers which would lie in the redundant region. If those registers have resets, then they can be marked as registers having redundant reset. Let's look at an example. In this example, there are two registers S1 and F1. Both of these registers are having the same reset signal RST and the reset values as 0. In this method, the reset value of one of the registers, say S1, would be forced on the output of the register S1. Based on this constant value 0, constant propagation would be done in the design. This constant propagation would make the register F1 redundant, which means that the value of the register F1 in the reset phase is not visible at the design output. Hence, the reset of the register F1 can be deemed as redundant. But this method requires designers to try out large number of permutations of registers on which the reset value is forced, and hence can take a lot of time in obtaining a meaningful set of registers from which resets can be safely removed. The other approach is based on X propagation technique. In this method, the designers can iteratively remove the resets of the registers and then make use of X propagation technique to ensure design functionality if it is still correct or not. In the X propagation technique, the registers without reset have an initialized state X, and then it basically evaluates whether X makes its way to the design output or not. If X cannot reach the design output, the reset is redundant, otherwise it is not. This method also suffers from long runtime and is impractical for modern SOCs, which can have millions of registers. So clearly, there is a need for an automated method. Now we would look at the sequential analysis and its applications. The identification of redundant reset is also based on the sequential analysis techniques. Sequential analysis is a process of multi-cycle analysis of design at RTL level. Using the sequential analysis, forward and backward analysis of the design can be done to understand the logic relationship between the registers. One of the applications of sequential analysis is clock gating of registers. Using the deep sequential analysis of the design, all the opportunities to save power can be found. And for each opportunity, initially all possible enable conditions are generated. And among all the possible enable conditions, trade-off analysis is performed in terms of area, timing, and power. Based on this trade-off, the most optimal enable condition is chosen to clock gate the registers. There are various other applications of deep sequential analysis as well. Apart from traditional clock gating, memory gating, data computation, data read-write, among others, are some of the important applications. And by looking beyond register boundaries, deep sequential analysis finds maximum number of optimization opportunities to save power of the design. Now we shall look into the observability-based sequential analysis technique for clock gating. It would be good to understand this in detail, as our reset optimization solution, which is the focus of this webinar, is also based on the observability-based sequential analysis. In this circuit, when the signal VLD2 is low in a clock cycle, the value at the output of the register D2 would not be observable at the output of the mux, which means that the write which would have happened one cycle back on register D2 is redundant. Similarly, the write that would have happened 2 cycles back on register D1 would be redundant. This process of identification of redundant writes across multiple clock cycles is called sequential analysis of the design. Observability-based clock gating would identify these redundant writes and add a suitable gating condition for the register D2 based on the signal VLD1. And similarly, based on the signal VLD for the register D1. The redundant reset removal capability is also based on the observability-based sequential analysis. Observability-based sequential analysis works based on the concept of ODC conditions in the design. Let's look at what is the meaning of the ODC conditions. ODC, or observability don't care condition of a signal, is a condition under which the particular signal's value at a particular instant of time has no impact on the design's primary output. Or in other words, the signal's value is completely unobservable at that instant of time. For example, consider an AND gate with two supports A and B. The value of signal A will not be observable whenever value of B is 0 at the same time instant. Thus, ODC condition for the signal A would be B equal to 0 or whenever the value of the signal B is 0. Since the output of AND gate is independent of A whenever B is equal to 0. This can also be seen from the truth table. Similarly, one can compute the ODC condition for signal B from the truth table. The ODC condition for the signal B would be A equal to 0. In the context of the sequential analysis, all the ODC conditions are not functionally safe to be used. Let's now introduce the concept of functionally safe ODC conditions. In this example, there is a register FF which is driving the primary output port through the combinational cloud H, whose other input in the design is D. So the output O of this design at time t is a function of FF and the other input D. The functionally safe ODC for the register FF says that at any time t, if safe ODC for the flop FF evaluates to true or 1, then the design output would never depend on the value of the register at that time t. And it will not depend on the value of the register for all future time instances greater than or equal to t as well. In other words, if the safe ODC condition is 1 for a register at any time t, the value of the register at that time will never be observable at the design's output for all future time instances greater than or equal to t. Observability-based clock gating uses the concept of safe ODC to produce functionally safe gating conditions for the registers. The same concept is used for identifying the redundant resets of registers. Let's understand the concept of safe and unsafe ODCs with the help of an example. In this simple circuit, there is a register FF whose data input is driven by the signal in and the enable input by the signal en. This register is driving a mux which is controlled by the signal cell. The output of the register FF is observable at the output of this mux only when the value of the signal cell is equal to 0. Otherwise, it is not. Hence, the ODC for register FF would be cell equal to 1 or when the value of the signal cell is equal to 1. Now, with the help of the waveforms, we would look at why this is an unsafe ODC. Let's consider that the value at the input in of the register are 4 and 5 in the clock cycles 1 and 2 respectively. Also, the values at the enable signal is 1 and 0 in those cycles. So, at the output of the register FF, the values would be 4 and 4 in cycles 2 and 3. Now let's assume that the value of the signal cell changes from 1 to 0 in cycles 2 and 3. Because of this, the design output O would observe the value at signal in 2 and 4 in the cycles 2 and 3. Now, in the clock cycle 2, as the value of the signal cell is 1, the ODC for register FF becomes true. But still, the value at the output of the register FF in cycle 2, which is 4, is visible at the design output in a future cycle 3. If we use this ODC condition to shut off the write of value 4 on the register in cycle 1, it would result in a functionally wrong behavior. Hence, this is a unsafe ODC to be used. Now let's look at another example to understand what is a safe ODC condition. In this circuit, the mux select is driven by a register whose data input is driven by the signal cell and enable is driven by the same signal en, which is also feeding the register FF. Here the ODC for the register FF would be cell rec equal to 1. Now again let's consider that the input values of the register FF are 4 and 5 in the clock cycles 1 and 2 respectively. And the value of cell reg changes from 1 to 0 in cycles 2 and 3. For the value of register cell reg to change like this, the values at the input signal cell has to be 1 and 0 in the previous cycles 1 and 2. At the same time, the register cell reg has to be enabled, which means that the value of the signal En has to be 1 in clock cycles 1 and 2. If the signal En is 1 in cycles 1 and 2, it would now result in output of the register FF to be 4 and 5 in cycles 2 and 3 as well, which would in turn result the design output O to observe value 5 in cycle 3. Here we can see that when the ODC for the register FF is true, the value of the register in that cycle, which is 4, is never observable at the design output. And hence, this ODC condition is a safe ODC condition for the register FF. Now that we have established the concept of safe ODCs, let's extend this concept of identifying the property related to registers on whether we can eliminate the reset for these registers. So what is the additional condition for the reset value safety, or when the reset of a particular register is active? Formally, we can state the additional property required for reset value redundancy to be that the safe ODC of the register's output should always evaluate to 1 or be a tautology when its corresponding reset is active. The reset redundancy condition thus implies that if safe ODC is true for all time instances during reset, then the reset value forced on the register FF will never be observed at any time instance beyond the reset state at any of the design outputs, and hence can be considered to be redundant. Based on the additional property for the reset value safety, now let's look at when can a register be deemed as having redundant reset. The first property which is checked is whether the register has a non-zero safe ODC condition or not. If there doesn't exist any safe ODC conditions for the register, then the reset of that register would not be redundant. If the register has the safe ODC condition, then it is checked whether safe ODC is evaluated to 1 in the reset phase or not. This is obtained by applying the reset values of the registers participating in safe ODC conditions. If it does not evaluate to 1, then the reset of the register is not redundant. And if it evaluates to 1, then the reset of the register can be deemed as redundant. Let's understand this in detail with the help of an example. In this circuit, there are two registers F1 and G1 which are driving a mux through some COM logic. The mux select is controlled by the register S1, and all of these registers are having the same asynchronous reset signal R and the reset value 0. In this case, it can be seen that the safe ODC condition for the register F1 would be S1 equal to 1, while the safe ODC condition for the register G1 would be S1 equal to 0. Now let's apply the reset value of the registers in the safe ODC conditions. For the register G1, if we apply the reset value 0 in the safe ODC condition, it would result in always false. This means that the reset value of the register G1 is visible at the design output and it cannot be removed. Hence, the reset of the register G1 is not redundant. Similarly, on applying the reset value 0 in the safe ODC condition for register F1, it results in a tautology. This says that the reset value of the register F1 is never visible at design outputs. Hence, its reset is redundant and can be removed. Now we shall put together the various steps of the proposed solution. There are essentially three important steps in the proposed solution. First step is to collect the safe ODC conditions for all the registers in the design in one go. The second step is to evaluate the safe ODC conditions of each register during reset phase. And then third and last step is to identify the registers having redundant resets. Let's now look at these steps in little more detail. In order to collect the safe ODC conditions for all the registers in the design, observability-based sequential analysis is performed on the design. This is a patented sequential analysis technique of power optimization in Power Pro platform. Using the observability-based sequential analysis, safe ODC conditions can be calculated for all the registers in the design in one shot. This is typically a very fast process. Then to evaluate the safe ODC conditions in the reset phase, the registers in the safe ODC conditions are substituted with their reset values. After the application of the reset values in the ODC condition, constant propagation is performed only in the ODC expression and its value is evaluated. Then a register is marked as having redundant reset if and only if the safe ODC expression evaluates to 1 or tautology. If it does not evaluate to tautology, the register does not have the redundant reset. Once we have figured out which register has got the redundant reset, the question is how to implement this change in the RTL. That is, how to remove the reset of the register. This is a sample RTL having 3 registers, each of which is having the same asynchronous reset signal RST. And let's assume that the reset of the register F1 has been found to be redundant. Now to remove the asynchronous reset of register F1 in the RTL, we need to first remove the assignment of this register in the reset sensitive block. And we need to add another reset insensitive block in which a non-reset assignment of register F1 needs to be added. This way, the assignment of the register F1 becomes independent of reset. Power Pro platform offers an automated solution to automatically identify redundant resets in the design. Now we would showcase some of the results of reset optimization feature of Power Pro on large industrial designs. The solution has been applied on many large designs for a variety of applications like multimedia, video processing, and other smartphone applications. All of these blocks are industrial designs having large number of gates. These suggestions from the optimization were manually applied on the RTL to remove the resets. The power savings were evaluated at the RTL level itself using Power Pro PA, which is an RTL power analysis tool. Finally, post layout savings were measured by taking the designs through the place and route flow. The matrices like utilized die area, number of buffers and inverters, post routing wire length, and total number of vias were compared. Let's now look at the results. This table of results focuses on reset load reduction. Here we are showing the results on 6 designs named from A through F in column 1. Column 2 is the total gate count of the design. Column 3 shows the percentage of registers which have resets in the design. Column 4 shows reset load reduction, which is the percentage of registers with redundant resets over the registers with resets. Finally, column 5 shows the runtime of the optimization on the corresponding design. The designs mentioned here are having thousands of gates, and the percentage of registers having resets are also very high. In the 4 designs, B to E, all the registers are having resets. Let's look at the reset load reduction in these designs when the solution is applied on these designs. We can see that as high as 72% reset load reduction from the optimization, which means that out of 100 registers with resets, on an average, 72 registers were found to be having redundant resets. Please note that runtime of the solution is well under 10 minutes for a 200K design which is design C here. Now, let's look at the flow used to substantiate power savings expected with the reset optimization due to picking up of smaller text cells for registers, which would typically consume less power. Original RTL was taken through the standard RTL power analysis flow by using PowerPro PA while providing the necessary tech libraries, design constraints, and the corresponding FSDBs. Using the power analysis flow, the matrices like total power and area were calculated. Then the original RTL was reset optimized to get the optimized RTL. The reset optimized RTL was resimulated in order to generate the new FSDB. Then the optimized RTL along with the new FSDB was taken through the RTL power analysis flow. The matrices total power, area were compared with the original RTL matrices. This table captures the results pertaining to power and area savings. To do a very thorough evaluation of the savings, this experiment has been performed with technology libraries from 3 different ASIC processor nodes: 55 nanometer, 28 nanometer, and 14 nanometer. Thus, for each of the 6 designs, sequential power savings and design area savings are there for each of these libraries. These are the results with the 55 nanometer library. We can see that as high as 22% sequential power savings and 2% design area reduction can be realized by reset optimization. Then these are the results with the 28 nanometer and 14 nanometer libraries. Here also, we can see there is a significant sequential power and area savings. These are in the range of 2 to 8%. As can be seen, sequential power savings are more pronounced for 55 nanometer process technology. However, there are still quite substantial for 28 nanometer and 14 nanometer. So now moving on to the gains post place and route. To establish the speculated advantages of reset optimization post layout, this is the flow that was used. Both the original RTL as well as the reset optimized RTL were taken through OSS to generate the gate level netlist while providing the necessary tech libs and design constraints. Place and route was done using Olympus while providing the necessary SDC, LEF, and DEF. Matrices collected and compared post layout included total instance count, area, buffer inverter count, total wire length, and number of vias. Let's first look at the reduction in the buffer and inverter counts. On an average, there has been around 2.8% reduction in buffer and inverter counts, and please note that it has been as high as 6.4% reduction, which is significant. In terms of utilized area reduction, it has been 1.5% on average and maximum of around 3%. We have also seen considerable reduction in the percentage wire length and number of vias as well. Benefits from having a small reset network and registers with smaller sizes have clearly manifested post layout. Finally, we arrive at the conclusion of the webinar, where we would like to summarize the key takeaways from the session. Large reset network leads to routing congestions, large rush current in the reset phase, and high register power and area of the design. Existing techniques to remove redundant resets are manual and time consuming. PowerPro provides the capability to identify the registers with redundant resets. This cuts away the need for painful and time consuming iterative process of reset removal, which has so far been used by the RTL designers. The proposed solution provides up to 22% reduction in sequential power and up to 3% area saving, and also up to 70% reset network load reduction. Post layout matrices like utilization, buffer count, wire length, number of vias also show significant improvement.